Hello everyone, Matthews here again, and today we're going to do a full review of AP Physics 1. So right now in this exam season, the AP Physics 1 exam is going to be different from what it's going to be next year. So this AP exam review, it includes everything from this year, but it also includes one extra topic, fluids, which will not be on the exam this year, but for any year beyond the AP exam in 2024, for the foreseeable future, this review should be fully cohesive and include all the topics. So here are all the units that we're going to go through. Kinematics, forces and translational dynamics, work, energy, power, linear momentum, torque, rotational dynamics, energy and momentum of rotating systems, oscillations, and then fluids. Fluids is not going to be included on this year's exam, as I mentioned before, but it is going to be on this year's AP Physics 2 exam, 2024. But it's going to be on the AP Physics 1 exam in 2025 and the years beyond. So now let's dive into kinematics. So first, we're going to go over scalars and vectors. Scalars have magnitude, while vectors have magnitude and direction. Because vectors have magnitude and direction, vectors can be modeled by an arrow. So the size represents the magnitude and the arrow points in the direction of the vector. And here's some examples of scalars and vectors. Speed and distance are both scalars, while velocity and acceleration are vectors. We'll go over these more in depth on the next few slides. And one thing you guys also need to know is that two vectors in the same direction, you can sum them by just adding their magnitude, and two vectors in opposite directions, if you want to do vector addition to them, you'll subtract them. This makes sense, right? Because two things in the same direction, they'll double, add on together, but two things in the opposite direction, they'll subtract. It intuitively makes sense. And here are some important terms that you all need to know. So for AP Physics 1, just treat all objects as points until we get to rotation, but for now, just assume that all objects can be treated as single points. Also, here are some important definitions. Displacement is referred to the change in position and is a vector. It's a vector because it's the final position minus the initial position. The direction shows if you went to the left or to the right, or depending on how you define your system of reference of the initial position. Velocity is the change in position over a certain time. Think of velocity as just displacement over time. How much you displace over a given time interval per second, usually. Average velocity will be over a long period of time, generally over long distances of long displacements as well. Instantaneous velocity will be during an instant, so a really short time. Average acceleration is the change in velocity over a period of time. So how much velocity changes over a period of time? Think of acceleration to velocity is the same as velocity to displacement. Instantaneous acceleration will be at an instant, a short amount of time, the change of velocity over a short amount of time. And an acceleration object will have its velocity changing. So if an object is accelerating, that by definition, that means its velocity is changing. And here are some units. So position, the SI unit is just meters. Velocity, meters per second. Speed, also meters per second. Acceleration, meters per second squared. Now time to represent motion. A changing velocity essentially just means that the object has an acceleration and that an object is either slowing down, speeding up, or changing direction, as velocity is a vector. Here are three important equations you guys need to know. Final velocity is equal to initial velocity plus acceleration times change in time. So the final velocity is the initial velocity without the acceleration plus however long you accelerate at and the acceleration. And that'll be the final velocity. And the units all add up too, because the unit for acceleration is meters per second squared. The unit for time is seconds. So if you multiply them, you just get meters per second, which is a unit of velocity. Here also, so final position is equal to initial position plus velocity times time plus 1/2 ht squared. So the final position is equal to the initial position, and then assuming then you add vt, and then you also add 1/2 at squared. And that's how you get the final position. This last equation, Vs squared is equal to Vi squared plus 2a change in displacement. All these equations relate two variables, or a few variables, right? The final equation, you relate the final velocity, initial velocity, displacement, and acceleration. The second equation, you relate the positions, velocity, and acceleration, and time. The first equation is simple. You just relate the velocity, acceleration, time, and final velocity. And these equations, they all work assuming a constant acceleration. If the acceleration is not constant, then these equations will not work, essentially. These equations will not be valid. And the acceleration due to gravity is 9.8 meters per second squared. So if you want to use these equations when someone's in free fall, that's the acceleration you will use. Okay, continuing. On a position time graph, so essentially you graph the position on the y-axis as a function of the time on the x-axis, the slope will be velocity, and you also have to include the sign. This makes sense intuitively, right? Because velocity is just the change in displacement or change in position over time, which is displacement over time. On a velocity time graph, the slope will be acceleration. This also makes sense for the same logic as before. And the units match up. Meters per second is meters per second and is the unit of velocity. Meters per second divided by second is meters per second squared, which is the unit of acceleration. And the area under the curve of a velocity time graph will equal displacement. And you also have to include the sign, as both are vectors. The area under an acceleration time graph will be the net change in velocity. And again, you include the sign as they all are vectors. And again, as stated earlier, you can use the units to check it out. And all of these assertions will be validated, which is nice. All right. An object's, excuse me. An object's velocity and acceleration might be different using different reference frames. So if I'm at one reference frame, but then I'm accelerating in a different reference frame, the velocity and acceleration might be different. So using logic and vectors, you can just determine the relative values of velocity in various reference frames. For example, let's say a train is moving right at 10 meters per second, and I'm moving right at 4 meters per second. In my reference frame, since I'm also moving right at 4 meters per second, the train from my POV is moving at 6 meters per second right. But if I was just still and not moving, the train would be moving at 10 meters per second right. So now I'm going to go over vectors and motion in 2 dimensions. In 2 dimensions, vectors can be broken into vertical and horizontal components. And motion in 2 dimensions can be done by analyzing each dimension separately. The velocity in one direction will not be changed by the acceleration in another dimension. Like the x component of velocity will not be changed by the y component of acceleration. That just doesn't make sense. So in projectile motion, the horizontal velocity will have no acceleration, so it remains constant. We're assuming no air resistance. So let's say you chuck a ball up and forward. The horizontal velocity will always be the same because there's no acceleration, but the vertical velocity will be influenced by the acceleration due to gravity. And then you use the kinematics equations with this knowledge to solve projectile motion problems. Just treat the y-axis and the x-axis differently. For the x-axis, just do constant velocity So position is equal to velocity times time. The horizontal velocity, which is the v cosine alpha, where alpha is this angle, as shown in the diagram. And for the vertical component, you can find the time it'll stay in the air by using the kinematics equations, with the acceleration as g and the velocity, starting velocity, as v sine alpha. Now I'm going to go over unit 2, forces and translational dynamics. So objects defined inside a system determine the system's properties. You define a system, and sometimes you can define it as a single object, but sometimes you can define it as many objects. Systems can interact with the outside environment, which will result in a transfer of energy and possibly mass. The center of mass is the average position of all parts in the system, weighted according to their masses. The center of mass along one axis will be the sum of all the masses multiplied by the relative position. So think of each mass on a line, each mass times the relative position, each mass times the relative position, multiply all of them. Add all of the multiplied values up and divide that by the sum of all masses. That would be the position or the location of the center of mass. It's sort of the weighted average of all the masses based on their positions. You can also model the system of many objects and just treat it as a single object at the center of mass. Forces and free body diagrams. Forces are vector quantities that describe interactions between objects and systems. That's really all forces are, but there are many types of forces, so it gets complex. And you all need to know that a system does not exert and will never exert a net force on itself. Another system must be exerting the net force on it. This just doesn't make sense. How can you exert a force on yourself, right? And contact forces involve touching. Contact forces are a type of force, and they're pretty common, right? Whenever you touch something, it's a force. And that contact force is due to the effect of interatomic electric forces. Free body diagrams are diagrams which show all the forces exerted on the system, and use the diagram, find out the net force, and you can calculate acceleration of the system through that. And the unit of force are newtons in honor of Sir Isaac Newton. Okay, here's an example of an FPD. So this guy, he's pushing a block, and the block is moving forward as shown by the velocity vector. So in the free body diagram, obviously there's the force of gravity down, but since it is not accelerating in the y direction, the force of the normal force must balance it out completely, which is why the two vectors are equal on the FPD. And then there's a F push, which is the forward force. And I didn't mention it, but I'm assuming that there's friction, right? Assuming that the surface is not perfectly smooth, so there's some friction that opposes it. But the frictional force has to be less than the F push force because we're assuming it is accelerating in the direction of the F push. But if it wasn't accelerating and it was just constant velocity, then it would be equal FF and F push. Here's another example FPD, but on a rotated axis. So in this FPD, let's assume that the box is in equilibrium. So that means there's no net force, there's no acceleration, and there's a constant velocity, which is, yeah. It can either be 0 or it's moving down at a constant speed. And looking at this diagram, right? Basically, we're going to shift our axes in the normal force direction. So the Fn is perpendicular to the surface. So that's the direction of Fn. Fg is straight down, right? But you can break that up into two components, Fg cos theta and Fg sine theta, as shown here. And then we're assuming that there's a frictional force that opposes the Fg sine theta, otherwise it wouldn't be in equilibrium. And as you can see here, all the net forces are balanced in the x direction and the y direction. Now we're going to go over Newton's first law of motion. Newton's first law of motion states that an object in motion will stay in motion unless there's an external unbalanced net force. Essentially, if the net force exerted on the system is zero, then the object will remain moving at a constant velocity and there will be no acceleration. Net force is just the sum of all the forces acting on a system. And static equilibrium refers to a stationary object, which is still in equilibrium. Dynamic equilibrium refers to an object moving at a constant velocity, and constant velocity still implies equilibrium because there's no acceleration and no net force. In 2 dimensions, the system velocity will change in the dimension that has the net unbalanced force. For example, in projectile motion, the velocity in the y direction is changing because of g. But in the x direction, we're assuming no air resistance, the velocity is constant. So the net force is zero. So I'll always split up the 2 dimensions and treat them separately when analyzing. Newton's second law. The net force exerted on a system is equal to the mass of the system multiplied by the acceleration of the system. That's essentially Newton's second law. F net is equal to ma, where the F net is in the direction of a. The units of force, newtons, are kg times meters per second squared. This is obviously because F net is equal to ma, the units of mass is kilograms, units of acceleration is meters per second squared. And the velocity will only change if there's a net force acting on it, because F net is equal to ma, right? If there's a net force not acting on the object, then a is zero, so the velocity will not change. Otherwise, the velocity will change. Now I'm going to go over Newton's third law. So every force is said to have an equal and opposite force exerted on the other object. For example, let's say I push a table, right? The table exerts the force back on me in the opposite direction. Now you will not be wondering, why don't the forces cancel out? It's because they're acting on different objects. I'm pushing the table is pushing me. So even though I'm pushing the table, right? The table's there's nothing balancing the table from my push, and the table is pushing me. And forces of objects are defined in one system, and they will not change the overall center of mass. So if forces are defined inside the system, the center of mass motion will stay the same velocity, because it's internal to the system. Now I'm going to go over tension force, which is the result of forces that hang from a string, chain, cable, or similar system from a hanging object. So in tension force, we assume that an ideal string has no mass. Otherwise, the equation that we use would not work. And we assume that tension force is the same throughout the entire string. If a string has a mass, this above statement cannot be true. So the tension force cannot be the same throughout the whole string if the string has a mass. An ideal pulley has a negligible mass and rotates around the axle with no friction. We'll go over pulleys in a bit, but yeah, just know that that's the condition for an ideal pulley. And on the right is a free body diagram of an object hanging by a string. There's a ft downward and ft upward because of the string, and since it's not moving, it's in equilibrium, so the forces are balanced. Now I'm going to go over pulleys. It might seem there's a lot on the slide, but I'll break it down. So we're assuming this is a pulley, right? There's M1 here, M2 there. And then drawing, excuse me, drawing the forces on this itself, basically, there's the force of gravity, which is why M1G is pointing downward, M2G is pointing downward. And we also need to know that the force of tension opposes it. And it's the same tension on both sides. So T is upward, T is upward. So let's assume that M2 is bigger than M1. If M2 is bigger than M1, that means M2 is going to accelerate down, while M1 is going to accelerate up. And writing equations for that, M1A is equal to T minus M1G. M1A is going to be in the opposite direction as M1G because M1A is accelerating upward, which is why M1A is positive and M1G is negative. And now for M2A, M2A is going to be in the same direction as M2G because M2 is accelerating downward. And it's in the opposite direction as tension. So you solve that equation, you solve for A, and that's the formula you get for acceleration of the ideal pulley. Gravitational force. So Newton's law of gravitation states that there's an attractive gravitational force between any two objects, and the forces will be described by this equation shown. Fg is equal to g m1 times m2 over r squared, where r is the distance between the center of mass of the two objects. And also note that Fg is also equal to m multiplied by lower g, and that lower g we'll go over later. And the big G is just a constant, and it's on the equation sheet. And since the big G is so small, 10 to the negative 11, for you to really accelerate and feel the force because of gravitation, the masses have to be extremely large, which is why you feel the force of gravity on Earth, but not from like a pencil that's standing near you, because the masses are too small. And planet movement is also governed by this gravitational force. This is the reason why planets orbit different planets. Also note that because any mass can have gravitational force, that means every mass creates a gravitational field around it. An object's weight is equal to m times g, and on Earth, g is equal to 9.8 meters per second squared, and g will change in different areas and planets. And sorry, not planets. Different areas and planets, g will change, but mass is always the same. So now we're going to go over a quick derivation of connecting the Newton equation of gravity to this equation and solving for lowercase g. So we know, let's say there's a person of mass m1 on a planet. We know his weight is m1 lowercase g multiplied by lowercase g. And we know we can also rewrite that as g m1 m2 over r squared, where m2 is the mass of the planet. And basically you can solve for lowercase g. And you get lowercase g is equal to big G m2 over r squared. M2 is the mass of the Earth, r is the distance between the center of masses. And m2 is creating the field. And on Earth, this equation will be 9.8 meters per second squared on average. Oh yeah, basically be 9.8 meters per second squared. All right, now you guys also need to know what apparent weight is. Apparent weight is essentially just the normal force exerted on a system, or think of it as how heavy you feel. So that means during free fall, assuming no air resistance, normal force is zero. So apparent weight is also zero because you feel no weight. That's why you feel like flying. That's why it feels like you're flying. Inertial mass, so mass has two properties, right? Mass can be thought of as, in Newton's terms, as resisting change, or in gravitational terms as gravitational attraction. And through experiments, scientists found out that inertial mass using inertia equations and gravitational mass using gravitational equations are always proven to be equal. And now here is a diagram showing apparent weight. So let's say this guy's in an elevator. He's accelerating downward at an acceleration of a. Drawing the free body diagram, Fn has to be smaller than Fg because he's accelerating downward. That means mg minus Fn is equal to ma. Therefore, in this scenario, Fn is smaller than mg because Fn, if you rearrange it, Fn is equal to mg minus ma. So in this scenario, apparent weight is smaller than usual, so you feel light. But if you're going up, for example, you'll feel heavy if you're accelerating upwards on an elevator. Now I'm going to go over friction. Kinetic friction occurs when two objects move relative to each other, resulting in resistance. So there are two types of friction, static and kinetic friction. Friction is always exerted opposite to an object's relative motion. This makes sense intuitively, or from like past experience. And note that friction does not depend on the contact area. The equation for friction is just a coefficient of friction multiplied by normal force. For kinetic friction, it's the coefficient of kinetic friction multiplied by normal force, but for static friction, it's the coefficient of static friction multiplied by normal force. And as we mentioned earlier, normal force is just the perpendicular force exerted on a surface, and the coefficient of kinetic friction just depends on the two surfaces in contact. Static friction occurs between two objects which are not relatively moving to each other. That means they're stationary. Static friction is therefore an adaptive force. It's always equal to the force exerted on the object, which friction force is opposing. Until the force exerted is greater than the max frictional force, static frictional force, then it turns to kinetic friction. And always note that that usually the coefficient of static friction is generally greater than the coefficient of kinetic friction. And yeah, so looking at the static friction equation, so frictional force has to be always less than or equal to the coefficient of static friction multiplied by normal force. It's never going to be greater than that because that's the max static friction. Spring forces. Ideal springs have negligible mass and exert a force equal to negative k times the change in x. K is the spring constant, and a higher spring constant means a higher force applies for the same change in length. This makes sense as shown by the equation. If k is higher, then you need a smaller change in x to result in the same force. And note that the force exerted on an object is always toward the spring's equilibrium position. So if it's compressed, that means the force is outward. Or if it's stretched, that means the force is inward. Circular motion. So why does circular motion occur? That is due to a centripetal force, which causes circular motion, and the centripetal force is always directed to the center of a circular path. Therefore, centripetal acceleration must also be directed to the center as a result, because force and acceleration are always in the same direction. Centripetal acceleration is equal to v squared over r. Therefore, centripetal force must equal to mv squared over r, since force is equal to mass times acceleration. An object moving in a vertical loop requires a minimum speed to maintain circular motion, and that minimum speed is equal to v is equal to square root of g times r. If it does not maintain this minimum speed, then it will not be able to move in a circle. And tangential acceleration just refers to the rate that tangential velocity changes. And tangential velocity is simply the object's linear speed at any point in motion. So not its angular speed, but the linear speed. Excuse me. The net acceleration is just the sum of centripetal and tangential acceleration. And since centripetal acceleration is inward, tangential acceleration is perpendicular, you'll have to use a vector sum to find the net acceleration. And here is the top view of a diagram of circular motion. Let's say I'm spinning this ball in a circle. So let's say the ball is being spun faster, right? If the ball is being spun faster and faster, that means the tangential velocity is increasing. That means there's tangential acceleration. And if the ball is being spun slower, that means tangential acceleration is in the opposite direction as tangential velocity because it's slowing down. Circular motion continued again. So the time to complete a full rotation is just known as the period. It's measured in seconds. The time to complete a full rotation around the circle and get back to the starting point. The rate at which an object completes rotations is known as frequency, and frequency is 1 over the period. And that also means period is 1 over the frequency. The period is essentially just the circumference, 2 pi r, divided by v, where v is the tangential speed, and it should be constant in circular motion. So yeah, that period equation is just distance over speed because he's going around the whole circle one time divided by the constant speed. For a spatial object in uniform circular motion, it's always going to be caused by gravitational attraction. And that means the period is equal to the square root of 4 pi squared times by r cubed divided by big G multiplied by big M, where M is the mass of the Earth or the mass of the thing that's orbiting something else. So like, let's say a satellite's orbiting Earth, M is the mass of the Earth. Now on to unit B, work, power, and energy. So what is kinetic energy? We hear it all the time, right? But what does it really mean? Kinetic energy is just energy due to motion. And for translational kinetic energy, meaning non-rotational, moving in a straight line, kinetic energy is equal to 1/2 mv squared. Energy is a scalar. That's why v is squared, right? Because if it was a vector, the v squared would show no unit, which won't make sense for kinetic energy. For velocity, systems might have different kinetic energies with different reference frames, as with velocity. So in one reference frame, the kinetic energy might be higher than in a different reference frame. Work. Think of work just as the transfer of energy into or out of the system, or how much energy is transferred into a system by a force exerted over distance. So there are two types of work done by conservative forces, meaning path independent, and work done by non-conservative forces, meaning path dependent. Path independent forces are like potential energy. So the potential energy at two varying points just depends on the difference in relative position and not how you got there. For example, let's say I have a ball at a height of 2 meters. Let's say I move it around different places and bring it to a height of 4 meters. The change in potential energy is just it's just the 4 and the 2, right? It doesn't matter how it got there. But friction, which is a non-conservative force, let's say a ball is rolling down, or not a ball, let's say a cube is rolling down a ramp and has friction on the ramp. The cube rolls down extra distance, goes around different places. It's more negative work is going to be done, meaning it's non-conservative force because it depends on distance as well. Work continued. The formula for work is just FD cosine theta. Theta is just the angle between the force and the distance vectors. Therefore, when theta is equal to 180, work is negative. When theta equals 90, work is 0. So the only component of force exerted parallel to distance does work. It cannot be perpendicular. Work is a scalar, but there's still positive and negative works. Positive works just means that energy increase in the system, and negative works means that energy decrease in the system. The work energy theorem states that the net work done on a system is just equal to the change in kinetic energy of the system. And you can use this to calculate either of those. And the units of work are just the units of energy, which are joules, which is just newtons times meter. Also note that the area under a force displacement curve gives the net work done on the system. This makes sense, right? Because work is just force times distance. And displacement accounts for the net work done. Potential energy is the energy associated with the positions of objects in the system. Elastic potential energy in an ideal spring is just 1/2 K times change in x squared. It's similar to the kinetic energy equation, so it's easy to remember. Gravitational potential energy is mgh, or in planet systems, minus g, m1, m2 over r. The first equation assumes a constant g, which is the case for people on a planet. The planetary equation is negative. As the further planets get away from each other, the less negative the GPE gets, so it increases and becomes closer to 0. But the closer the planets are, the more negative it gets, so it decreases. The total GPE of the system is just the sum of PE between every single two objects in the system. Conservation of energy. Sole objects as a system can only contain kinetic energy and cannot have any form of potential energy. This makes sense, right? Because for potential energy, you need a reference point. But like if there's just one object, you can't really have any form of potential energy. If a system does not interact through non-conservative forces, that means energy will always be shifted between forms and will not really be lost as heat. For example, friction is a non-conservative force, and energy is lost as heat when friction does work. And mechanical energy is just the sum of all Ke and Pe in the system. The total energy in a system will always remain constant when there are no external forces doing work, as the change in energy of the system is just the work done on it. That means the total mechanical energy in the system will be constant with no external forces doing work. Here's a diagram showing conservation of energy. So this is the roller coaster, right? Has a mass of m, height of h. So initial potential energy is mgh. And let's say it moves all the way down. At the bottom, the kinetic energy is going to be 1/2 mv squared, assuming no friction and air resistance, because all the initial gravitational potential energy converts to kinetic energy. So mgh is equal to 1/2 mv squared equals the total mechanical energy in the system. Let's look at this diagram now. Let's say this ramp, height of h, and let's say it's rough. Basically, the initial potential energy is just mgh, right? But as it slides down the ramp, the box, there's work done by friction. So at the bottom, it's going to be mgh minus ffkd. Frictional kinetic friction force times the distance traveled. Mgh minus that is equal to 1/2 mv squared. If there was no friction, it would just be the same as the last equation. Power. Power is defined as the average rate at which energy changes. Average power equals the change in energy or work divided by the time interval. And the units for power are watts or joules per second. Yeah, so power just equals to work over time, which is equal to ft cosine theta over time. But actually, distance over time is just speed, or I guess velocity, depends on how you view it, but you can just go with speed. So really, power is equal to fv cosine theta, where theta, again, is the angle between f and d. Linear momentum, unit 4. Here are the basics of linear momentum. Linear momentum is a vector, and it just equals the mass times the velocity. The direction will always be in the same direction as velocity because mass is a scalar. And you can analyze the change in momentum of different collisions, including explosions, by just analyzing the initial and final momentum states. The unit of momentum is kg meters per second, because mass times velocity, unit of mass is kg, unit of velocity is meters per second. So now we're going to define a term called impulse. Impulse just refers to the change in momentum during a certain time period. So final momentum minus initial momentum. Impulse also equals just F net on a system multiplied by the time. Impulse also is a vector quantity and has the same direction as the force exerted on the system. Note that the net area under a force time graph will give the impulse, and the slope of a momentum time graph equals the net external force. Look at this logically, right? Force times time is equal to impulse, so the net area will obviously equal the impulse. For the slope of a momentum time graph will equal external force by you can validate that by rearranging the impulse equation. So let's connect this to Newton's second law. F net is equal to ma, which is equal to change in momentum over time, or impulse over time, which is equal to m times change in velocity over time, assuming the mass doesn't change. And you can connect all of these together. Now I'm going to go over conservation of linear momentum. So for a system of objects, you can just think of that system as just one object at the center of mass moving at a constant velocity. The velocity of the center of mass is just the sum of all the momenta divided by the sum of all the masses. This equation is similar to the position center of mass equation. And the velocity of a system center of mass will remain constant if there are no net external forces, even if collisions occur inside the system, because then the momentum of the system will be constant, even if they're collisions inside the system, because there's no work done outside the system changing the energy. And that means the velocity of the system center of mass will be the same. Linear momentum will always be conserved in a closed system, meaning no net external forces. Momentum inside the system can shift between objects, however. This makes sense, right? Because let's say many objects are defined in the system, but no external forces are driving the system. The momentum can shift between the individual objects as long as the total momentum of the system is constant. And because of Newton's second law, the impulse on one object is equal and opposite to the impulse on another object. Well, this is really because of Newton's third law, because every force has an equal and opposite reaction force. So the impulse on one object will have the same force on the other object, and the time exerted is the same. And momentum can also be transferred to the environment under an impulse. Elastic and inelastic collisions. Elastic collisions is when no kinetic energy is lost. So the initial kinetic energy equals final kinetic energy. The kinetic energy of the system must not change. That means it'll be inelastic, right? But individual objects in the system can have their kinetic energies change. But in inelastic collisions, the kinetic energy of the entire system decreases. So the total kinetic energy of all the objects before will be greater than the total kinetic energy of all the objects afterward. This is because some of the energy is lost as heat or sound through the collisions in the non-conservative forces. Perfectly inelastic collisions refer to those where objects will stick together after the collision and move with the same velocity. But momentum will always be conserved in both of the collisions, assuming there are no external forces on the system. Also, think of it mathematically, right? When two objects stick together, the final kinetic energy is always going to be less than the initial kinetic energy. This is because kinetic energy has a higher dependence on velocity because it's v squared and only a regular dependence on mass. So that means when they stick together, their velocities will change and their masses will become bigger, but the momentum is still going to be constant. Work it out on paper to fully understand it. But yeah, that's the main gist of it. And here is an example, right? So let's say there's this 5 kilogram object going to the right at 5 meters per second. And then there's this 3 kilogram object going to the right at 1 meters per second. So the initial momentum is just 5 times 5 plus 3 times 1, which is 28 kilogram meters per second. And that's also going to be equal to final momentum because momentum is conserved. The initial kinetic energy is just 1/2 mv squared for both the objects, which is 64 joules. So the final momentum is equal to 8 kilograms because we're assuming a perfectly inelastic collision, so the masses combined, 8 kilograms times the final velocity. The final velocity is equal to 3.5 meters per second. So the final kinetic energy equals this. And as you can see, it's clearly less than in the initial kinetic energy in an inelastic collision. Torque and rotational dynamics. First, we have to define what a rigid system is. Rigid systems are defined as systems that hold their shape, but different points move in different directions in the system. So the overall shape of the system will be the same. It won't like fold or break, but like different points in the system, they can be moving in different directions. Rigid systems can be translated or rotated. And the distance between any 2 points in a rigid body is fixed, no matter how it is rotated or translated. Think of a ruler, right? We're assuming it's not going to break, so the distance between any 2 points will always be fixed. Yeah, and essentially that just means it will not break via rotation or translation. And you can think of anything, as I said earlier, hard to break, like a basketball. This whole unit of rotation, it assumes that we are working on a rigid body. Rotational kinematics. Angular displacement is the change of an angle in radians, theta final minus theta initial. Counterclockwise rotation is considered positive, as while clockwise rotation is considered negative. This is just convention. Angular velocity is just the change in angular displacement, or I guess just angular displacement, since displacement is a change over time. There are a lot of parallels between rotational kinematics and normal kinematics, linear kinematics. Angular acceleration is the change in angular velocity over time. And as I said earlier, these are analogous to their linear counterparts. And all of the equations for kinematics are going to be the same in rotational kinematics, assuming a constant angular acceleration. You just replace the velocity with omega, which is angular velocity, acceleration with alpha, which is angular acceleration, and position with theta, which is angular position or displacement. And yeah, rotational motion. So for a point, a distance r from the center, if the system rotates at angle theta away from that point, the distance covered by that point would be r theta. This is sort of like, think of geometry in math, where r is in radians. It's essentially that. I mean, theta is in radians, essentially that. Tangential velocity for a point, a distance r away from the center, is just r times the angular velocity. And tangential acceleration for a point, a distance r away from the center, is r times the angular acceleration. So essentially, you just multiply r by each of the angular components to get the tangential components. And the tangential components just refer to like the sort of the linear aspect of it, perpendicular or parallel. I mean, I guess at a tangent to the point. So as you can see in this diagram, right? A distance r away is going to be at the top. And you can find the tangential velocity, tangential acceleration, and tangential or linear distance covered. Just multiplying r by each of those values, angular, acceleration, velocity, and displacement. So what is torque? Torque is essentially just an analogy to force, but in rotational motion. Just as force causes changes in velocity and causes angular accelerations, torque causes angular accelerations, which cause changes in angular velocity. Sorry, I think I messed up. So forces cause accelerations, which cause changes in velocity. Torques cause angular acceleration, which causes changes in angular velocity. And one thing you must note is that the force must not be along the axis of rotation line to cause a torque. Because if it is, then it'll just be a normal force and it'll linearly accelerate the system. Let's say you have a ruler, right? If you push, the ruler rotates, let's say the ruler is just in the air, it'll rotate about its center. If you push directly at the center, it's just going to move flat and it's not going to rotate. But if you push any distance away from the center on the ruler, it'll rotate a bit. The lever/moment arm is always perpendicular from the axis of rotation to the line along the forces acting. And force diagrams are essentially kind of like the free body diagrams, but they'll include torque. They show forces in the relative location relative to the axis of rotation. And these force diagrams can help you find net torques on a system. And so what is the equation for torque? Torque is equal to force cross product R, where R is the position vector from the axis of rotation to force. This is in contrast to work, right? Work is F dot product D. This is a cross product. And a cross product, you can just think of it as F times by R sine of theta, where theta is the angle between F and R. Therefore, if theta equals 0, that means there's no net torque. Because if theta equals 0, that means the force is just acting along the axis of the rotation line. So here is the visual of torque. Let's say there's this disk, and the center of mass is there, and it has a radius of r. In the first scenario, torque is equal to Fr sine theta, but since it's pushing along the axis of rotation directly, theta equals 0. So torque is just 0 because it's not going to rotate, it's going to linearly accelerate. But let's look at the second example. Here, torque is equal to Fr sine 90 degrees because the angle between F and R is 90 degrees. That means the torque is just going to be Fr and it's going to rotate. So torque is always a maximum when the angle is 90 degrees. So sine will be 1. Rotational inertia. So just as there's mass in linear mechanics, there's also a rotational inertia in rotational mechanics. So rotational inertia is just defined as resistance to a change in rotation, or how much resistance a system has to the change in rotation. So for any mass at a perpendicular distance from the axis of rotation, the rotational inertia will just be I is equal to mr squared. Therefore, the total rotational energy of the system, not rotational energy, sorry, the total rotational inertia of a system is just the sum of all the masses multiplied by the perpendicular distance from the axis of rotation. The total moment of inertia, or rotational inertia, is the sum of all of the mr squareds for every mass in the system, a distance r from the axis of rotation. And this is a brief theorem the exam wants you to know. The parallel axis theorem. It essentially states that if the moment of inertia is equal to the moment of the center of mass plus md squared. So the moment of inertia at some point is equal to the moment of inertia of the center of mass plus the mass at that point times the distance squared, where distance is the parallel distance between the final point we're looking at from the center of mass location. And also note that the moment of inertia at the center of mass does not have to be 0 if the axis of rotation is not at the center of mass. So it all depends on the axis of rotation and where the center of mass is located. Here's a diagram showing what we covered on the last slide. So let's say this is a ruler, right? It's rigid body. The center of mass is defined here. And it has a mass here, m at the center of mass. And there are also two masses at the end point. And let's say this mass is defined as 1, this mass and position is defined as 2. So the moment of inertia at position 1 is equal to the moment of inertia at position 2, which is equal to the moment of inertia at the center of mass, plus mr squared, as you can see from this equation. Rotational equilibrium. Rotational equilibrium means that the net torque on a system is 0. So that means there's no angular acceleration. This is analogous to normal equilibrium in linear mechanics. Because no angular acceleration means the constant angular velocity, and a non-zero angular acceleration means a changing angular velocity. And relating to Newton's second law, angular acceleration is just equal to torque over moment of inertia. To account for signs when determining net torque, we use the same convention. We said a positive torque if it makes the system angularly accelerate counterclockwise, and a negative torque if it makes the system angularly accelerate clockwise. So here's an example where we're calculating the net torque on a system. So this is a force F pushing upward, distance r, force F pushing upward, and force F lowercase f pushing downward at a distance of big R. And this is the axis of rotation, and it's also the center of mass. Yeah, let's just assume it's the center of mass, assuming that all the mass is uniformly distributed. So the net torque of the system is just the sum of all the torque. So let's calculate. This first torque on the left side, it's making the system rotate clockwise. Think of it logically, right? You push it upward, it's rotating clockwise. So since it's rotating clockwise, we're going to set it to negative FR. This this torque on the rightmost side is making it accelerate counterclockwise. And if you push it here, think logically, it's going to accelerate counterclockwise. So this is going to be a positive FR, as shown here. And this final torque, pushing downward, is going to make it angularly accelerate clockwise. So it's again minus Fr. And these two net torques cancel out. So it's just the net torque is negative Fr. Magnitude is just Fr. And since it's negative Fr, that means it's going to accelerate clockwise. And one thing to note, here, since all the forces are perpendicular to the system, I just ignore the sign because the sine of theta is just 1. So it's just going to be Fr, the magnitude of torque. And now I'm just going to go over the units in this unit. The unit of angular displacement is radians. Angular velocity is radians per second. Angular acceleration is radians per second squared. Torque is Newton meter. Moment of inertia is kilogram meter squared. And also note that 1 radian is just equal to 57.3 degrees, or 180 degrees divided by pi. Unit 6, energy and momentum of rotating systems. So now that you all know some basics of rotation, now we're going to go over to energy and momentum. So it's pretty cool, right? First two units, we did like the basics, kinematics and forces. And unit 5, the one we just did, those were the kinematics and forces of rotation. Then we moved on to energy and momentum of linear systems, and now we're going over energy and momentum of rotating systems. So just as there's linear kinetic energy, there's also rotational kinetic energy. And this is just equal to 1/2 moment of inertia times omega squared. This is pretty easy to remember since it's analogous to the normal kinetic energy. The total kinetic energy of the system just equals the rotational kinetic energy added to the translational kinetic energy. And rotational kinetic energy is also a scalar quantity, since all energy is a scalar. Note that a system center of mass can still be at rest while having a rotational kinetic energy. A center of mass can be at rest because it's not linearly accelerating, but points can still be rotating if the center of mass is at rest. Think of a ruler, right? Let's say it's on the ground. It's not linearly moving, but it's just spinning in a circle. The center of mass is at one point, but it's still rotating. So torque can also do work. The work done by torque equals torque multiplied by angular displacement. And the work done by torque is the change in rotational kinetic energy of the system, similar to the work energy theorem that we discussed earlier. Therefore, the area under the curve of a torque angular displacement graph just gives the net work done by torque. Angular momentum and impulse. So just as there is linear momentum, there is also angular momentum. The magnitude of angular momentum of a rigid system about an axis is L, which is a symbol, equals I omega, which makes sense. It's analogous to normal momentum. And the magnitude of angular momentum about a point is R mv sine theta. So think of this as it's a point moving around a point in a straight line. That'll be R mv sine theta. The selection of the axis of rotation is key as it determines the angular momentum. Angular impulse is torque times the time interval, which is analogous to normal impulse. Angular impulse will always be in the same direction as the torque, because angular impulse is change in angular momentum and torque causes the change. Angular impulse also equals the area under the curve of a torque versus time graph. Angular impulse is also just the change in angular momentum. So angular momentum final minus angular momentum initial. The net torque is the change in angular momentum over time, which is just moment of inertia times angular acceleration. The net torque therefore must equal the slope of the graph of angular momentum as a function of time. Just as linear momentum is conserved, angular momentum is also conserved. The total angular momentum of a system equals the sum of all angular momentum components about that axis. and changes in the system's angular momentum will be due to interactions between the system and its surroundings. Otherwise, if there's no interaction between the system and its surroundings, the angular momentum will be the same. The angular speed of a non-rigid system can change without the total angular momentum changing. As if the system is non-rigid, the moment of inertia can be changing. So essentially, the angular momentum can still be constant, even if the speed is changing, because in a non-rigid system, that means it's wobbly, it'll break, it can break up. That means the moment of inertia will be changing too. It's just sort of common sense. So what is rolling exactly? Obviously, we've all seen like how tires roll, we've seen bowling balls roll, but what is it? So first, note that the total kinetic energy of a system equals the translational kinetic energy plus the rotational kinetic energy. Rolling without slipping refers to like a wheel-like object rotating on the ground, and the part of the wheel in contact with the ground, this is very important, is instantaneously at rest relative to the ground. So that means it's going to be a static friction force. And this is only true when it's rolling without slipping. When an object is rolling without slipping, the change in center of mass position equals r times the change in theta of rotation. And the velocity of the center of mass equals r omega. Acceleration of the center of mass equals r times angular acceleration. And all of these are only true when it is rolling without slipping. So when will it not be rolling without slipping? So rolling without slipping means that there's no kinetic friction force, there's only a static frictional force because it's instantaneous relative to the ground. So the frictional force does not dissipate any energy. And all these equations and stuff described above are not true when a system is slipping while rolling. Because that means if it's slipping, that means there's going to be a static, or I'm not sorry, how do I say this? A kinetic friction component that will dissipate energy. So here's a diagram showing what I mean. So this is rolling without slipping, the first one. There's a frictional force in the other direction that makes a torque, and we're assuming the object rotates in the clockwise direction. And you can validate that as this frictional force will cause the torque to make it rotate in the clockwise direction. Rolling with slipping is essentially this ball, or this round object, it's gonna frictionally move, it's gonna like slide here, slip. That's what the slipping part means. And there's a kinetic friction force as it's slipping because it's not instantaneous relative to the ground. And that kinetic friction force points in the left direction, the opposite direction of motion, and will dissipate energy. So yeah. Now I'm going to briefly go over the motion of orbiting satellites. So the motion of satellites also observes conservation laws. Therefore, the total mechanical energy of the system is constant. The sum of gravitational potential energy and kinetic energy are constant, and the satellite's angular momentum relative to what it is orbiting is also constant. The kinetic energy and gravitational potential energy of the satellite can change, but the sum must be constant because the total mechanical energy will be constant. The escape velocity of a satellite is the velocity such that the mechanical energy of the system will be zero. And when deriving that, the escape velocity is equal to the square root of 2gm over r. Oscillations. So what is simple harmonic motion? Simple harmonic motion is a type of oscillation, and an oscillation just refers to something sort of going out of position, coming back into position. Think of it like intuitively. An SHM, simple harmonic motion, is a case of periodic motion. So there always must be a restoring force. Think of a pendulum. It is always accelerating back to its equilibrium position, which is the center. So there must be a net force pointing back to that center. The magnitude of the restoring force must be proportional to the displacement from equilibrium for it to be simple harmonic motion. So on a spring, MA is equal to minus K times the change in X. the net force is equal to the spring force, which is equal to minus k change in x. And the negative sign indicates that it's a restoring force in the opposite sign of displacement from the equilibrium. So that means the restoring force and acceleration points towards the center and the equilibrium position. And that equilibrium, that must mean S net must be equal to 0, because change in x equals 0. And for pendulum, it's the same as in the spring. At the center, there's no net force. And for a pendulum, the restoring torque is proportional to the angular displacement. And yeah, so you all might be thinking, right? If at the center the net force is 0, how is this still able to move? The net force is 0 at the center, but it still has a velocity. So it still moves to one side, and then there's a net force again. So frequency and periods in SHM. The period is the time it takes for a full oscillation. So it starts at equilibrium, oscillates, and ends back at equilibrium. That's the period. Frequency is just 1 over the period, aka the number of oscillations per second. And two common simple harmonic motion systems that they want you to know of are an object spring system or a pendulum system. The period of an object spring system is just 2 pi square root m over k, where m is the mass of the object suspended by the spring. The period of a pendulum system is 2 pi square root L over g, where L is the length of the string and g is just g, acceleration due to gravity. These equations will be on the equation sheet, so you don't have to memorize it. And this equation assumes that the pendulum is displaced by a small angle, known as the small angle assumption. And period and frequency are always going to be independent of that angle. Because as you see in the equation, there's nothing about the angle in the equation. So the period and frequency are independent of the angle displacement. And here's just a diagram showing some forms of simple harmonic motion. This first one is the pendulum system. It's displaced the angle theta from the equilibrium, and this is the length L. And it'll be in simple harmonic motion now. This second system is a vertical mass spring system. We're assuming the equilibrium is down there, so the spring is compressed a distance of change in x upward. So it's also going to go through simple harmonic motion. This last system is a horizontal spring system. So we're assuming no friction, but there technically can be friction. You'll have to account for that. And let's say the equilibrium position is at the end here, but this system's also been compressed by this change in xi value. So it will go through simple harmonic motion. So how do we analyze simple harmonic motion? For an object in SHM, displacement will be modeled by either one of two equations. First of all, x is equal to a cosine 2 pi ft, or x is equal to a sine 2 pi ft. So it's modeled by a sinusoid. A is the initial displacement, f is just the frequency, and t is as a function of time. It's a function of t. X is a function of t. And a cool thing is these equations can represent displacement, velocity, and acceleration. Also note that frequency is just 1 over period, where period is just t. So you can replace frequency with 1 over t in any of these equations. Minima, maxima, and zeros are all aspects of SHM for displacement, velocity, and acceleration. And recognizing these points can help in describing the motion of a system in SHM. Also note that changing the amplitude will not change the period. Think of it this way, right? If you increase the amplitude, then there's more distance to travel, so the force is larger. So the time, the period will end up being the same. So it'll cancel out. Let's go through a few diagrams. So let's say there is a system in simple harmonic motion, the equilibrium at the center, and it's been stretched a distance a away from the equilibrium. Or yeah, a distance of a minus equilibrium from the equilibrium. And there are these three graphs. One of them represents displacement as a function of time, one of them represents velocity, and one of them represents acceleration. So how would you go about figuring out which one represents each of them? Well, first of all, let's assume that it starts off, we're assuming it starts off not at the equilibrium. So at t equals 0, it's at A. So that automatically rules out the upper right one. And now out of these two, how do you tell which one's position and which one's X and which one's not? So to do that, we're assuming, since it's displayed to the right, that its initial position is positive in respect to the equilibrium. So that means it's going to be this first one, bottom left. Position starts out positive, then it decreases. It'll reach 0 at the equilibrium. Then it'll go to the right, reach its maximum amplitude B here. Then it'll go back to the equilibrium. And then it'll go back to the starting point. So this bottom left one represents the position as a function of time. How do we find which one represents acceleration? Well, to do that, the graph of acceleration will be opposite of the graph of position. Because if it's displaced by a positive amount, the acceleration is going to be in the opposite direction, negative. And since it's initially displaced at a position of A, and it's away from the equilibrium, that means there's going to be a negative acceleration in the opposite direction at time equals 0. So it cannot be this upper one. And that means it has to be this bottom right one. And note how it's the exact opposite as the position graph. In shape, at least. This is because acceleration is proportional to net force, and net force is equal to minus kx. And finally, that means this upper right one must be the velocity graph. This makes sense because at position A at the start, velocity is going to be 0. Because at endpoints in simple harmonic motion, velocity is always 0. And then at the other endpoint, velocity will also be 0. And yeah, that's how you can determine which graphs represent which ones. Energy in simple harmonic motion. The total energy of a system exhibiting SHM is just the total potential energy plus the total kinetic energy at any given instant. And this value will be constant due to conservation of energy. At different times, either U and K will be higher, and they will change around the SHM oscillation. But the total mechanic energy, assuming no friction and outside forces, will be a constant. Therefore, KE must be a max when potential energy is a minimum, and the opposite must be true as well. So when kinetic energy equals 0, potential energy is at a max, and the total mechanical energy of the system equals potential energy at that instant. So U is equal to 1/2 Ka squared, where A is the max amplitude stretch, and the total mechanic energy must also equal 1/2 Ka squared. And assuming no external forces, that value of total mechanical energy will be constant. Fluids. So if you're watching this video in 2024, this is not going to be on the AP exam, but for any year after this, fluids is going to be on the AP exam for the new revised framework. So first we need to define a few things. What is density? States of matter are determined by interactions between atoms and molecules. Fluids have no fixed shape, but they have a fixed volume and a fixed density. And density just refers to the mass over the volume. So therefore, the unit of density is kilograms per meters cubed. And we assume ideal fluids are incompressible and have no viscosity, which is the sticky resistance of a fluid. And in fluids, we assume that we work with ideal fluids. Pressure. So pressure is just the magnitude or perpendicular force per unit area. Pressure is a scalar quantity. Think about it, like a needle hurts, right? Because it has such a small area. So that means the pressure is going to be high. But the bed feels nice, right? Because it's extended over a large area, right? The pressure is going to be very small. Pressure from a fluid is governed by the interactions of a fluid's particles and the surface. The absolute pressure, the total pressure, is just the initial pressure at some point, plus rho GH, where rho is the density of the fluid, and H is the depth down. P0 is the atmospheric pressure, and P gauge is just PGH. The P gauge is just the new added pressure, not including the atmospheric pressure. And here's a diagram representing what I mean. So let's say there is this container of water. At the top, there's just atmospheric pressure pushing down. And at a depth of h, the pressure of the water at this point, the bottommost point, will be from the weight of all the water molecules above it. So it's just the atmospheric pressure from the top plus rho gh, the pressure from the water. And we're assuming rho is the density of the fluid. Therefore, as you go lower in a container of water, the pressure increases at the lower you go at that point. Now I'm going to go over the basics of fluid. Buoyant force is the net upward force on an object. And the buoyant force is just made up of the forces particles interacting with the object provide. So in water or in the fluid, it'll be from the fluid pushing up against the object. The buoyant force just equals to rho v g, where rho is the density of the water, and v is the amount of water displaced. So it's really just the mass of the water displaced. Essentially, buoyant force is the force exerted on an object due to the weight of the fluid displaced. Yeah. So density times volume is equal to mass, right? So it's just mass times g, which is the force. Density of the liquid displaced times by volume of the liquid displaced multiplied by g. That's the buoyant force on an object submerged. Now I'm going to go over conservation laws in fluids. So differences in pressure between two areas cause the fluid to flow from an area of high pressure to low pressure. Always know that a fluid will flow from the area of high to low pressure always. And in fluid flow, we always assume that there's only laminar flow and not turbulent flow. Laminar flow refers to smooth, nice flow. And also due to conservation of mass, in a given area, the amount of water going in must always equal the amount of water going out during a given time interval. So the volume over a given time is constant. Therefore, the area times the distance over time is constant, so area times velocity is constant. This is known as the equation of continuity. It takes that the area at one point times the speed of the water at one point equals the area at another point times the speed of the water or the speed of the fluid at a different point. Therefore, smaller openings, the speed will be faster than in bigger openings, assuming laminar flow and an ideal fluid. Bernoulli's equation describes conservation of mechanical energy in fluid flow. So the initial pressure plus rho g y1 plus 1/2 rho v1 squared is equal to final pressure plus rho g y2 plus 1/2 rho v2 squared, where rho refers to the density of the fluid. This will also be on the equation sheet, and you can just use this whenever you need it. Torricelli's theorem states that the velocity is equal to square root of 2gy. The speed of the fluid will be equal to the square root of 2gy coming out of a hole at a depth of h. As shown in this diagram, let's say there's a depth of y. The speed the water comes out at will be equal to square root of 2gy. Thanks for listening. Let us know if you have any questions in the comment section, and best of luck